Hi, everybody. Welcome to our the Battery Pack Discharging Monthly Series, Topic 5, Who's Doing It Right? Cool Science, Part 1.
So if we move on to the next slide, we'll kind of give you our foundational basis here. So what we really do, guys, is just aim to support conversations across different players in the field of energy storage, kind of speak the unspoken to battery science, a little bit of the tribal knowledge. And then, we want to talk about things you don't really see in the lab that, a lot of companies won't discuss. But having said that, we are, as we try to share some of these non-confidential lessons learned, we are extremely we want to avoid any kind of litigious event. So really here, everything shown in this presentation is publicly available online. And a lot of the opinions or deductions expressed are solely those of me and Aubert. We'll try to share as much information as we can and derive some conclusions, but remember, those are solely ours. Aubert?
Sure. And so finally, this took us a very long time to do, and we apologize. It's mostly my fault for my poor video editing skills, but we now finally have all of our presentations that we've previously done, which there's 4 others on our Who's Doing It Well series and our Autopsy of Oxus Energy, all available as PDFs for presentations, and also finally all the videos are up, which was the big thing. So what we're hoping to do from this is just basically allow people who actually go join other talks to actually then still be able to enjoy what we present. We know there's lots of options at these, and we just want to make sure people don't miss out. So that was the initial plan for the videos, and it just took us 8 months to get our act together enough to have them already. So these resources are available, and just for anyone who's asking the questions right now, because I see the chat has some things, but I can't view it. This presentation itself is available up on the Battery Brunch website under Notes. It should be available, these links should be available there right now if people want to come here right now and check and see if you can get to the videos and PDFs. We'll add all the PDFs to these as we have them to present, and then the videos within a week or two of us doing these presentations.
Awesome. Going on. So we wanted to also just support the community as much as possible. I know as everyone joined, they were all talking about jobs and everything else. Ironically enough, this is me being a nerd. My wife asked where I could get jobs because she was applying for jobs. So I thought the easiest thing was to parse every job site and create a list of every job by every company for battery engineers. And what we want to do is we update this once a month and share with you the data. And this here to link is to just show you where it is. So kind of a quick graph. We can kind of go over jobs by state. If you flip it over, we can do jobs even by city. This is all in the link. You can't read anything, I'm sorry. And then jobs by company. So I kind of in the top right put the highest performers here. You can see a lot of the companies here, General Motors, Apple, Factorial, they're probably the biggest hires or the biggest companies hiring right now. But really what I want to draw your eyes to is on this next slide, which is if you look over just the dates of 3 months, the battery job market's actually doubled in size, basically. So this is data I grabbed from LinkedIn, and we'll keep these graphs going and all this data going, and hopefully add more analytics over time. But basically, yeah, it's a good time to be a battery engineer, everyone. I think that's the main takeaway.
Okay, and just real quickly, so when we go over companies, we tried to have sort of a set in stone grading scheme, and so this is sort of how we do it. We go over a couple categories: surviving the valley of death, engineering into the box, tech matching, pain points, and then just do we like them? And we give them a grade between 0 and 5. We've only given one person a 0 so far, and that was Oxus, who died in the valley of death. And I think we have given out a 5 before for somebody truly outstanding in a category. But this is not university grading where if it's not an 80 or 90%, it's bad. To us, 2.5 is like a good average. So we with this grading metric, 2.5 plus is sort of neutral to positive, and 2.5 to 0 is neutral to negative. So, in terms of the categories, so surviving valley of death, if you're not familiar with this, it's a very common concept in the Bay Area where a lot of companies die in the valley of death. And it's basically your ability to fund yourself as you go from research and development all the way to product launch, commercialization, where you're at your point where you've spent the most money and made the least, and then be able to work your way back up this wonderful trough here over time to break even as a business and eventually be profitable. So the goal is to hit this quadrant up here where you actually have had success as a business and are profitable and have paid off all of your investors or loans. And that's sort of the goal of all for the most part, the goal of companies to get to.
Awesome. And then, engineering to the box or not, in reality, guys, there's a lot of steps around making a battery. There's the mining, the extraction, the processing, the purification, the assembly, to all the way to just it going into a pack. What pack, and can you get into that pack? And when really what we're talking about this category is how many of these processes does this new technology disrupt, right? So for example, we talk a lot about solid state, but solid state is one extreme where you have to literally re-engineer how you apply electrolyte and how you get it into the cell and all the manufacturing equipment associated with that. So you are not only reinventing or adding a new technology and material that you have to figure out and scale in manufacturing, but you're also disrupting a lot of the manufacturing practices down the line. Conversely, a opposite end of that would be someone doing like a silicon anode, where it's relatively plug and play for the most part. You're putting it into a slurry, you are casting that slurry on a piece of copper. Every machine is currently in manufacturing is built to support that. You may have some other issues like scaling of that material, but your disruption in terms of that box that is the engineering and manufacturing side of batteries, you are not disrupting. As far as pain points go, really in this category, what we want to talk about is foreseeable problems. As someone takes something, they make a couple grams of it or 100 milligrams of it on this laboratory reactor, and then they go to bench scale and they're making a few hundred grams, and then they're going to pilot and they're making kilos. And what we want to highlight is the challenges and the potential issues these companies may face in that due to how they either A, make their material, or B, the processes they use, right? So the way I like to think about this is, how you mix something in a small beaker will not translate to how you mix something by the thousands of liters, right? So like really the grading scale here is, will they run into material issues at the scale? And if they don't have material issues or they aren't a materials company, then this becomes a little bit more of a, as Aubert pointed out, and I don't know, because we may not know exactly what pain points they have.
Okay, and the next one is one of our favorite categories, which is matching technology to market, debunking the silver bullet. This is something that we just see universally across, most industries, but the battery industry in particular, where people say, I have a battery that does A, I have a different battery that does B, and I have a third battery that does C, and so I have a battery that does ABC. And that is not the case. Battery engineering is all about trade-offs as you switch different materials with different properties and configure them in different ways for different goals. So a nice way of looking at this is the battery in a Tesla is a very, very different battery than what's used by a soldier in the field in a hot desert for mobile communication. They're just very, very, very different. Same thing for the battery in a drone versus the battery in a consumer electronics device. Right? One wants very high power for a very short period of time. One wants very long cycle life and, energy density too, but basically very long cycle life at low rates. And so this is something we really try to look at a lot, is to look at whether companies are actually matching their technology to appropriate markets and whether they're actually being truthful about the pros and cons of their technology as well in how they do that.
All right, and then this is kind of our, what we would call our most subjective and qualitative category. This is the do we like them? Hold on here, gonna just, I don't know if I can't mute. Do you have mute privileges, Aubert?
I can. Who was it?
It's okay. Anyway, So this is our qualitative category. It's kind of like a do we like them? So really what we're doing here is we're looking at the company and we're seeing how they present themselves, right? As fellow battery engineers, right, what we want to do is really understand the technology and make sure that you are presenting yourself in a manner that is not representative of the technology that you're using. So here we kind of have 9 subjective categories, which we kind of say, are they doing this? Are they not doing this? And then sometimes the honest answer is just, we don't know. A great example of this is Scylla had a lot of I don't knows because Scylla is very tight-lipped about a lot of the work they do.
And one other thing that we both can't recommend this enough, but there's a link to the bottom of an article that came out last year, 10 Ways to Fool the Masses When Presenting Battery Research. If you haven't read that, I highly, highly recommend it. We shamelessly stole a couple of these directly from them. They just did a very good job of breaking it down into kind of the categories of things that people do to be tricksy with how they present their data. Yep. And that's one of the big problems right now in batteries, and actually in general in batteries, is that there's a lot of theoretical versus actual calculations, marketing hype, and other things like that that do make it kind of hard to actually tell what's working and what's not, and what the pros and cons are. Okay. So, Jeff, you want to get this one?
Yeah, so kind of like on the last line about misrepresentation or anything else, we also recognize that at the Battery Brunch, there is a lot of adjacent industries, be that investors or other companies that are adjacent to the main battery field. So really what we do here is we recommend investors to ask these questions when they're talking to a company, but on the exact opposite end, we ask that startups or battery companies look at these questions and prepare for them. The way we view this is we are trying to help you prepare yourself for what an investor might ask, and we are trying to also educate the community as a whole on the investor side such that they know what questions they should be asking. So this is kind of a gift to both ends, and what we want to do is just make sure everybody's on the same page about what's important and we don't get misrepresentation, right? A great example of this is your data from a coin or is your data from a pouch? They're very different, and they have very different representations of actual performance in the cell.
And is it one extremely well-performing cell, or is it the average for a 100-cell data set, right? Okay, so at last, what you've all been waiting for. These are the two companies we're going to be presenting today. This is our cool science companies, 1 and 2. So the first two we're going to look at is Sulfate Technologies and Ampcera. They're both companies that Jeff and I think are really cool, and so we're really excited to talk about them today. So you want to get Sulfate and I'll get Ampcera?
Sure thing. So if you guys noticed the trend today, it's electrolytes. What we've talked a lot about silicon, we've talked a lot about solid state, but what we wanted to do is do two kind of orthogonal approaches to each other. We all currently use liquid electrolytes in our batteries, our standard carbonate system. Here we're talking about someone taking a liquefied gas and someone doing purely just a solid. Sulfate Technologies is out of San Diego. They've been around for about 7 years. They're an early stage startup, not a ton of funding. Really, their big jazz here is high voltage lithium metal and broad temperature windows, and that's if to just kind of make a simplified version of this, liquefied gases don't freeze easily. So if you're talking about increasing the temperature range by which a cell can operate, a liquefied gas is a very interesting approach to that problem. Additionally, it is also, as I will get into later, an interesting approach to how to increase electrode density.
Okay. And the other company is Ampcera. So some of you might be familiar with them. I believe Hui presented for them a few months ago, either the January one or one of the last ones last year. And Ampcera does a lot of different solid state sort of R&D scale materials. And they're kind of unique in that they work in a very broad range of things in solid state on a lot of the different components. But while they do work to integrate those together, what they also primarily do is they make them and supply them to other companies for their R&D. And so they give solid state electrolytes and solid state sputter targets and solid state polymers and oxides and all kinds of other things to other people as tools for them to help solve the, how to make an actual solid state cell work or different types of solid state cells work. They're also an early stage startup, and one of the things that's unique about them is they're selling materials already, which is fairly rare. And so anyway, we'll tell you more about both of these and kind of go over the pros and cons of them for normal. So first up,
all right,
Sulfate.
Yep. So Sulfate, as we mentioned earlier, they're really an early stage startup. So around 7 years is where they've been. They were founded in 2015. Actually, it's founded by two professors at UCSD. We're talking about Cyrus, the last name blanks, and then actually Shirley Meng worked on this project with them a lot. And if you look at a lot of the initial publications by the lab groups, it's a Shirley Meng and Cyrus duo on all their publication papers. Since then, they've basically in total gotten about $16.4 million to sustain their operations. Really, when we were looking at all their financials and we were looking at whether they're surviving the valley, we came down to one interesting thing, and this is something that a lot of battery companies don't answer clearly, which is, do they plan on manufacturing or licensing, right? That is going to really dictate the outcome of how we approach them in terms of, are they doing things well, right? So right now, all we can really say is they're a 2.5, which really means we just don't know. They're firmly in the valley. They haven't crawled out. They're just in there existing. They do have 3 job openings, so it means that they are liquid and able to at least attract talent, and they have the cash flow, or they're cash flow positive right now for that. But we don't really know much more. We would adjust this score, honestly, if we knew they were going manufacturing or licensing. Licensing, we would probably give them slightly higher, just because if you're licensing, suddenly the cost burden associated with proving out your technology drops significantly. But if their end game was to be a battery manufacturer, right, the financials they have at this point would put them significantly lower, because there's no way they could sustain the pricing of all the equipment associated you need for even just getting a pilot line up. A pilot line, a good one, is going to run you in excess of what they currently funded anyways. So that's kind of where we landed on them for the surviving the valley. Aubert, any comments?
Other than, they did an okay job on getting different government grants and funding, which I always rate really highly. It's always a very good thing for startups to do in terms of just funding the research they're already doing, getting good publications and recognition for it, and it does help you raise investment. So for me, that sort of, it's a 2.5 plus, but we don't have a metric for that. But that I did like that they've got, that they've been consistently doing grants year to year.
All right. Engineering into the box. So let's talk about liquefied gas electrolytes. So this is all publicly. You can read it in their information in their publications and papers. What they do is they use difluoromethane with LiTFSI, and then they use acetonitrile, actually. So it's 1 part liquefied gas, or basically a compressed gas into a liquid, with LiTFSI as the ionically conductive salt. And then what they do is they use acetonitrile actually as a dispersant, similar to what you would find in the printable inks category, where you add in a little bit of a co-solvent or a co-liquid to act as a dispersant, and that's really what helps elevate their ionic conductivity. The real reason there is in terms of just they need to be able to move ions fast enough, and you can't do that with just a pure liquid compressed gas. But as far as engineering into the box goes, this one is actually relatively high. You aren't disrupting a ton of things, right? So you're basically injecting right after the cell has been built. So all of the assembly and manufacturing processes prior to electrolyte injection are completely untouched, right? It is my understanding that they currently just buy cells from Argonne National Labs, and they basically take in 18650s that are pre-made, just without the cap. They haven't gone through the injection and the cap welding process. But there's going to be basically 2 major issues that they as a technology are going to run into. One is just the cap welding, right? If you have a gas and your gas is liquefied or compressed, as the cell reaches temperature, that gas is going to want to expand and become, or that liquid is going to want to, that liquefied gas is going to want to expand and become gas phase again. If you rely on a traditional crimping mechanism where you just have a gasket and a crimp, that may not be sufficient over the long-term duration of the cell's cycle life to actually keep all that compressed gas inside the cell for the duration of its duty cycle. The second thing they're going to have to come in through that's going to be a little bit challenging is going to be really just the injection process, right? So when you have a compressed gas that is a liquid, you have to keep it extremely cold. Now, the act of making or liquefying or compressing a gas to a liquid isn't new. We all, most of the scientists in the room will have used liquid nitrogen. The technology already exists. It's already used in a mass scale, so that's not the issue. The issue is the cell has to be brought down to the temperature that the compressed liquid gas is, because if you are trying to fill the cell, and the cell is room temperature, and the thing coming out of the nozzle is that liquid gas, and it is sub-zero, it will just turn vapor phase on you immediately and go back to its gas phase. So the question here really is, when they do the electrolyte filling with this liquefied gas, are they going to be able, will they have condensation, right? The cell's running through an assembly line, you've cooled it down really hard. Once you fill it with the liquefied gas, you're going to get any kind of condensation on the cell, any kind of moisture buildup. Is the cell going to like being frozen, right? Like, these are really the 2 points that are going to be the big sticklers. And then you can't really weld, your tabs the way you used to, because suddenly you would be introducing heat into an area that is extremely cold, so that then becomes a challenge. We really gave them a 4.5 because the reality is, although they have a lot of these challenges around this one piece of tooling within the system that may have spiraling ramifications, overall, none of their technology is what I would call revolutionary in the sense that you're going to have to reinvent the wheel on several components, right? The technology to liquefy a gas is already here, compress a gas is already here. The technology to basically freeze something down is already there. So really it's, can you just alter this one piece of manufacturing to accommodate this new technology? So I rated them relatively high. Okay, as far as overcoming the pain points, so as far as there's a little bit of misinformation. So we did a bunch of searching around their website. A lot of their work actually shows them using lithium metal. So from the lithium metal standpoint, all their data indicates that they're getting about a Coulombic efficiency of 99.6, which, to kind of frame it in everyone's context, you need to be 99.999 to have a long cycling battery where you haven't skewed the N to P ratio so far off. But after scouring their website, what we actually found out is they're actually marketing this as a replacement to the current standard or state-of-the-art batteries. So this would be a direct plug-in replacement for carbonates. So that kind of changed our viewpoint on what pain points they'll face. So the ones that we can really think of is more of the supply network. It is one thing to have this really cool electrolyte, and then it's another thing of, can they get enough of difluoromethane to supply the amount of 18650s they want to have, and when do they actually hit cost parity of that compressed gas, right? And the processes associated with it. Is that a megawatt? Is that a gigawatt? Is that 100 gigawatts, right? Is there enough difluoromethane in the world to actually support 100 gigawatts of this technology? Another thing that is going to be really challenging them, and it's going to be a pain point, if their goal is to plug into existing technology, when they plug in is going to be a tangent point. And if the current state-of-the-art technology is outpacing them in for energy density and in terms of just like performance, the question will then become, is the benefits of a gas electrolyte, which are primarily related to safety and denser electrodes, going to be worth the hit at that orthogonal point of industry improving the overall cell performance, right? Most people don't like to step back on performance in trade-off for other features like slightly better safety, right? Gas electrolytes guys, they survive nail pen, crush, everything, because the gas just basically dissipates so quickly that you can never hit ignition. So it's really safe, but when you're introducing this as a pain point into the current state-of-the-art technology, you're going to have to make a performance trade-off. And industry is going to outpace their technology, and the question is, will they basically insert at the right time? Aubert?
Sure. So tech matching, I gave them a 5 out of 5 in terms of what they're going for, because for the most part, what they're doing is they're basically enabling low temperature performance in all of these spaces, and particularly for aerospace and defense. That is a huge deal, but it also comes in for other things. Marine batteries get very cold, especially things like submarines. Cars in the winter are a really big deal. Tesla performance, any EV performance, I just happen to know the ones for Teslas, drop dramatically in the cold. And for renewables too, if you've got a big battery bank sitting outside, deserts fluctuate between extremely hot temperatures during the day to extremely cold temperatures at night. And so it does make a big difference being able to have a low temperature, durable battery. And also from a safety perspective, as Jeff just mentioned, one of the big advantages of this is that, unlike traditional liquid electrolytes where they're punctured or exposed to air and then they catch on fire, causing the whole battery or pack to go off. Hopefully for these, the way that they're structured is as long as the gas can escape through the damage, they should be able to then combust. And so really their target, regardless of how else they're marketing it, what really their targets are is low temperature applications and safety. And I think for that, it's basically a perfect fit.
Yeah, I mean, if you look at it, guys, this isn't like they're using silicon, which has inherent problems. This isn't them using lithium metal. This isn't them using solid state. This is plugging into the current battery technology that fits already in so many different applications. That's why we gave them a 5, right? It's not like they have this new chemistry or material, this new material that has some inherent limitations. They are plugging into the existing anode-cathode configuration with the same amount of ionic conductivity that is in existing electrolyte systems. So,
and the last piece is it's somewhat apparent that they're getting lots of different types of chemistry cells and lots of different cell types, although they are mostly working on cylindrical. And so it does seem like something that's sort of very broadly applicable as sort of a new technology into many potential chemistries of batteries, fields of use, and applications. So anyway.
Yeah.
Hey, Jeff and Aubert, can I ask you a quick question here?
Sure.
One thing that always strikes me is the whole highly pressurized cells and stuff. Are the cells under pretty high pressure? And then it feels like intuitively that would be really bad for safety, but I think you guys are making the argument, and they're making the argument, that it's actually good for safety.
So,
is that right?
I can expand upon that a little bit here. So the amount of pressure that so there is one fundamental failure, which I think in our haste to maintain the time allotment we didn't achieve, but the cells can only go into 18650s or hard encased cells. They will not work in a pouch. Any application with a pouch will not work for this gas electrolyte. The safety aspect of it and the pressure aspect we can address first is the pressure. The amount of pressure these cells generate at elevated temperatures up to 80 C by their data is not even enough to break the seal on the CPID within the 18650. So it'll use the existing pressure safety mechanism and be compliant with that till 80 degrees Celsius without ever running into an overpressure of the cell. The safety aspect, I would argue, is extremely high, because the safety on this is going to become an issue where when does it vent? So let's just say we have a thermal situation where stuff around it's getting really hot, you're heating the gas inside, it keeps getting hotter, or maybe you're running into an overcharge where the gas is getting extremely hot. The CPID will break, all the liquefied gas will become gas phase and then just leave the cell. The dissipation difluoromethane is extremely light, so it's kind of like hydrogen leaking, right? Although hydrogen itself is relatively flammable and dangerous, the rate at which it dissipates into the surrounding atmosphere far exceeds the rate at which it can ignite. And that is the same thing with this cell, right? If you were to crush the 18650, before the electrodes can generate enough heat between each other to auto-ignite the gas is already dissipated out of the system.
One quick thing, just from a time perspective, I'd like to keep going so we can finish the first part of the presentation. We typically ask people to save questions for the end or throw them into the chat, and for everyone, we should have said this earlier, but the way these work is we typically present the whole first section, and then there's some announcements as we all go back in about 10 minutes, and then we come back and we field all your questions for the next hour or two. So please come back after the presentation is over, and we'd be happy to take your questions then. We really enjoy that part of it, but we need to keep going so we finish everything for this.
All right, so moving on. This is our do we like them? Honestly, guys, they're a big I don't know. I'm not going to spend a lot of time here. They have more question marks around these questions than they do have definitive answers. The ones we could say is, are they overhyped? Are they not overhyped? Yeah, they're not overhyped. They're not pressing press releases. They're not pressing outrageous claims. They're not, we found some research stuff where they had those charts where this is them higher than standard art, but that was in a research publication and it's not even on their website. They don't even claim numbers on their website. As far as changing the materials and stuff, they're agnostic to that, right? They aren't producing the NMC or playing the loading game or playing the cathode thickness game or how much you have or any of that stuff. And then as far as composition or any of that, they also, similar to number 6, they don't do any of that, right? They're getting a assembled cell and they're putting their thing in it and then they're sealing it. So they're really agnostic to a lot of these questions, which is kind of why they're unique. So, but to be objective, we gave them I don't know, because there isn't too much information out there. A lot of this has to be derived from their research publications, but we gave them +1 for the cool science fact. I think gas electrolytes are a really interesting or orthogonal approach to the solid state industry. They both kind of achieve to do the same thing, right? Which is add safety and be workable with lithium metal. And if you take a note from like FMC's stabilized lithium metal nanoparticles, right? They achieve stabilized lithium in a dry or in an outside atmosphere through gas phase deposition. So, I think this is just a really cool orthogonal approach. So yeah, I'm going to give them +1 for liking them. I just think they're different, and they're approaching this whole entire energy field very differently than what you see a lot of out of the big names that we see every day.
Okay, so let's jump to Ampcera. So Ampcera has also only been around for a short time, about 7 years. It's hard to exactly tell because not all the people that work for them show up on LinkedIn and other team places, but they have about 8 to 10 people. They've been around about 7 years. They've also done pretty well in getting grants, and they've had about $1 million of private equity that they got in about 2018. So what this tells me, because there's so little money in investment, is there's no public information on how much they make selling their materials, which I'll get to in a minute, but it basically means they have to be breaking even in order to fund what they're doing. They have 20 plus patent pending, both patents and applications in the US internationally. And I'll show some of the materials they're selling, but they're already effectively commercial and R&D stage for a lot of different solid state materials, which I think is really cool. So here's just a very small subset, but there's an enormous amount of different types of materials they have for sale, specifically on MSE. And these range from things like LLZO, garnet, PVD sputtering targets, to solid state electrolyte materials, to other solid state enabling materials. And we'll get to more of the technology as it comes forward, but I think it's really cool to see a small company basically selling a very high value, low size market, selling into that in batteries, which is just very rare. So I think this is, in terms of the other companies we've looked at, they're basically the only people who seem to already be doing something cool, interesting, and new that are actually at least breaking even, if not making a profit on it, in small scale and in solid state, which is incredible. No one is making money in solid state yet, so except maybe them. So I think from surviving the Valley of Death, we gave them a 4 out of 5. Just they're hitting all the right targets. They're profitable already. It looks like they're small and lean. They're doing patents. They're making lots of different materials, and they're actually selling stuff. Anything else, Jeff?
No, I think overall the main message above the table here, everybody, is I think we've all seen MSC supplies. If you're a startup, you've probably bought from MSC supplies. If you're in a research lab, you've probably bought from MSC supplies, and you're actually funding Ampcera when you do that. And that is why we gave them a pretty favorable score in surviving the Valley, because they have actually started a revenue stream. And once you've started a revenue stream, that really significantly enables your chances of succeeding. And on top of that, they get to harvest all the data from researchers and everything using their technology and use that to feed back into their development process. So I think, that's why we gave them a really high score.
So engineering into the box, they have a lot of different materials that they're working on, but basically, they've got, solid state electrolytes, other solid state materials, and items that enable solid state materials like sputter targets and so on. They've got 4 key patents, and basically their model seems to be develop technologies, sell the R&D products to people, which they make money on and fund their development, and then circle back and then patent more things and repeat. And so from an engineering into the box, we gave them a 3.5, which to us is very high, but might not look high, and I want to explain that really quickly. But basically, solid state in general does not engineer into the box for batteries. Almost every type of solid state materials require extensive supply, machine, tooling, processing, manufacturing, testing differences in standard lithium ion or lithium metal batteries. And so while solid state does not really engineer into the box, Ampcera is like a 4.5 or a 5 of engineering into the solid state box. So that's how we gave them that score. We think they're doing a fantastic job for what they are doing, but just in the industry as a whole, there's a lot of challenges in solid state, which leads us to pain points. So real quickly, actually, for this, for entering into the box too, we don't have a lot of time left on this, so I'll gloss, but basically there's been a lot of work in solid state materials over a very long period of time. There's a ton of different approaches, not just from a material perspective, but from a process and equipment perspective using those materials. And one of the things I think is very cool about what they're doing is they're working with so many different of these different materials. And it's, there's individual companies that pick one or two and just take them for a long shot. But they're working with all of them at sort of a middling level, and then therefore getting the advantages of all of the different technologies.
So, as the great Good Enough said, winter is coming. Pain points for solid state materials are exceedingly numerous. If we just take away what the best solid state material is, right? And there are several solid state materials that have very different properties that are meant for very different things and give very different benefits. The biggest issue with this is it's talking about making and scaling a brand new material and being able to reproduce that material over and over again at a large scale that is efficient and economical, right? Ampcera's biggest challenge is how are they going to go from making these small 1 kilo batches, which may be stoichiometrically somewhat varied.
I touched a button. I apologize.
Aubert.
I don't know what I did.
Right. So stoichiometrically differently, right? In normal science, when you are creating something that is a specialty product, you are allowed some amount of margin of variability, right? You could have a stoichiometric ratio for your LPS be like 0.5. Like, I'm making these numbers up, so don't quote me, but like 0.511, right? And you can tolerate anything from 0.4 to 0.6, from 0.9 to 0.2, or 1.2, and 0.9 to 1.2. As you get into larger manufacturing, they want those things tightened. And that's where the variability and the pain is going to come for Ampcera is, will their particle size be the same? Will they have the same particle size distribution? Will the crystallinity of each particle be the same? Will the surface energy of each particle be the same? Will it be stoichiometrically tight, or will it not be stoichiometrically tight? How quickly does it oxidize? What are the storage conditions? What is the shelf life? All of these things become a huge issue. So the reality is they're selling right now, and they're doing a really good job, but we don't know. This is a 2.5. There's a lot of pain that is going to come out of this.
So we have about 15 seconds left per slide, so we're going to go very quickly through the last couple, and then we'll come back afterwards and kind of re-go over them a little bit more during the question section. One thing to say really quickly here, though, is this 2.5 rating is not so much a critique of Ampcera. What they're doing or how they're scaling what they're doing a good job. It's how that is then translated into how do they get that into a gigafactory, which is they have to be able to pass it off to somebody else, and the challenges of their supply to them, to the other people, is where that 2.5 comes from. Okay, so I really didn't want to shortchange Ampcera, so I backtracked just a tiny bit. In general, and we mentioned this a little bit earlier, but solid state materials, at least early stage, until they have been fully commercialized and the actual final costs and cost to benefit ratios and performance are finalized, really fundamentally that they're going to be a more expensive adaptation technology. A lot of the manufacturing processes, especially for solid state things like PVD or CVD, they're not wide area, they're slower, and they're more expensive. Now, a lot of the technology advantages of solid state end up being much higher than traditional lithium-ion, lithium metal, whether it's for safety with hybrid systems, or whether it's just the pure energy density you can get when you really optimize it, whether it's the finite control you get over the materials. But basically, they almost have to be targeted to a high value, lower market size, where they're an enabling technology and can command a premium. And so that's sort of the issue, is how do you get it from where that is to start to fully commercial? So again, I just want to highlight that the pain points are not so much Ampcera's direct pain points, it's solid state batteries pain points. And what they're doing is sort of the first leg in the R&D and development and spreading the technology and giving people the early stage materials with one piece of the puzzle or solution that can be then developed on and invented upon and combined with other things in the system. But the road forward is going to be long, hard, and expensive until they get it to be producible in large quantity at low cost.
We got a chat here, and I'll address it right now. Guys, remember, safety is a relative term in the battery industry, right? Everybody says, oh, you're safe because you're using LFP. It's a safer, more stable chemistry than NMC, guys. Look, I don't know where you stand on this, but if you are on a 100 kilowatt hour battery pack versus an 80 kilowatt hour battery pack, that's still a lot of energy in a very small place that when it goes will cause damage, right? So nothing is absolutely safe, right? Trying to take a binary stance on whether it is safe or as safe as something else in terms of the end come failure mode, whether it can ignite or short or generate heat or catch fire is very hard to quantify, right? Cars are not perfectly safe. They are meant to be safe enough to get you out, right? So like that is the kind of the metric here. If you can delay the fire or the catastrophic propagation of failure,
or the scale of that failure,
even slightly, that will be seen as a safer technology. Remember, it's all about safer. It's not about absolutes.
Okay. So then back to technology, which is where we kind of sort of started shortchanging them a little bit. But again, we gave them a 4.5 because they have many different materials, and you can look up all of them with usually paper links and cost trade-off benefit links on MSC. But all of their different technology groups and products all have very different properties, and they're very upfront about here's the pros, here's the cons. If you want ABC and don't care about EFG, use this. And I really like seeing that, because again, it's just kind of refreshing having somebody be sort of a little bit more honest about the pros and cons of their technology and system and materials versus just touting the pros. And so I encourage people to go look some of this stuff up. It's really cool. A lot of the different solid state technologies.
Yeah.
Anything else, Jeff?
I mean, I just think this is cool, guys. Like, this is a battery company publicly putting out there, and granted they sell things, so there's a little bit more of an incentive to actually list what the person is buying, right? Because you have a consumer and they want to understand what they're buying. But like the fact that they're coming out here with spider diagrams and just showing like, you buy oxides, this is what you're getting. You buy sulfides, this is what you're getting. Like, I think that's really cool. I think like for a materials company to come out and show this and show the advantages or disadvantages and help remove the shroud, right? If you look at it, oxides are QuantumScape, sulfides are solid power, and back when we had the company owned by Bosch, starts with an S.
Scion?
No.
CO.
They were polymer composites, right? So like you can kind of see here kind of a mismatch of actually all the different solid state battery companies, and it's really cool that they just have this chart here saying, hey, look, these are what these materials do and what they do well.
And here's an example of exactly that. So this is directly from one of their marketing materials, courtesy of Hui. And this is an example of a garnet, and I think it's either a garnet. I forget the picture on the left, whether that's a sputter target. I think it's not. I think it's just an LLZO solid state material for use in batteries. But they talk here about here's the advantages, very clear advantages. Here's the challenges and problems, very clear, right? So if you want to use this, here's what it does. Here's what you need to be aware of. If what you're using it for can't deal with these challenges, don't use it. If you want these advantages, please do. And so, understanding the pros and cons of their own materials and being public with the disadvantages that's a huge plus in my mind. Also, so that's why we gave them 4.5.
Another reason for that, guys, remember, when we talk about realistic tech for their application, we're trying to be objective, right? Their application is a solid state battery, right? It is not an EV. It is not a car or like a plane. It's not a grid scale. Their end consumer, as Ampcera is the person making the battery. So are they realistic towards their tech for the application? 100%, right? They are realistic within this box, which is they are a material supplier to solid state batteries, which is inside of this bigger solid state battery box, which there's a lot of misinformation around what it is actually good for, right? So we gave them a high rating because in good faith, we can't say, well, they're solid state batteries aren't great for cars. That's not who they're selling to. They're selling to other solid state battery people. So they're 100% matching their market.
The other thing, and this is not 100% captured, other than maybe we're a little bit more favorable because of this, but the fact that they provide these materials, whereas most other companies are extremely close fists with what they have and how they work, and you can't get samples, it really lets other people tackle the other challenges inherent in solid state with good working baselines with repeatable supply to work from, and that's a huge deal in R&D. If you're having to deal with different materials every time you get them from somebody else and then try to do your own special thing on top of it, it's almost impossible for you to develop or innovate. And so I just see this as such a wonderful addition to the battery industry and the solid state development of the industry. So I'm pretty pro on them and what they do, which leads to, do we like them?
So, valid cell cycling conditions. We don't know. They're selling materials, they're not selling a battery, so there's not really a ton of information there. Anything is solid state, right? Yeah, well, okay. They're a solid state company, so like everything is solid state. As reproducible,
but for the only company where everything is solid state, it actually fits for them, and so that's my favorite part of this whole slide.
Right, reproducible cell data sets. They're selling materials, guys. We're not going to hold them to the burden of reproducible data sets. They're not trying to be a cell manufacturer, so we're just going to give it an I to know. Energy densities, basically the next three we gave them yeses because this isn't their thing. Actually, it is probably better to say, everyone, that this chart can't be accurately representative of Ampcera because they are not trying to make a battery. They're a materials company that happens to exist in the battery ecosystem. And I think they're doing that very well. And we gave them a 4. Once again, we're giving all the cool science people or people who we think are approaching the industry slightly orthogonal to a lot of the standard routes that we see today, right? Usually when we talk about battery companies, we talk about the Solid Powers, the Scion Powers, the Enovixes, the Scillas, right? That's when you talk about batteries, you're always talking about those companies. And what we think is the cool thing, or what really the cool science is like companies like this or South 8. They're very orthogonal, right? Their approach is very fundamentally different than someone who is trying to wrap everything within their umbrella. They're saying, we want to carve out this niche. This is the only niche we want to do, and we want to do this well. And this is what we're going to do. And we think that's really cool, right? I think, like, if you had the chance to be like, my job isn't to make a functioning cell. My job is to go make this cool new solid state material every day and then test out its properties. That has a far different pressure burden than if you're like, I got to figure out how to laser sinter this oxide layer, make it not crack during the manufacturing process, and get a couple thousand cycles at high C rate with very high capacity retention.
For low cost.
For low cost. 2% margins. Something like that, right?
In 3 months before our company runs out of money.
Yeah. So I think they're doing really well on this front. So if you go to the next slide, what we've kind of done is shown you kind of our spider diagram, right, where we think each company exceeds, and we give you kind of like the total average score at the bottom. What you can see is South 8 is 0.1 higher than Ampcera. Honestly, we do try to be as objective and quantitative in our assessments as possible. We try to frame everything in the context by what the company is trying to do and what the actual market industry is. The reality is you will see some of the slight differences, right? Ampcera sells things and they make money, so they're going to survive the Valley of Death better. Tech matching the silver bullet, right? Well, they're doing the right thing for their company, but they are within the box of solid state. So you have to kind of, realistically gauge within that. Whereas Ampcera or South 8 is realistically going for things that already exist. So this is how we overall rated them, but similarly, and we do this with all companies, and this is available for all companies, we just really want to highlight their strengths and their weaknesses. And I think like everybody here could agree, nothing is perfect with each other, and there's always going to be a plus or a minus somewhere. But having said that, if we rate you and you are part of one of these companies and you feel like we could change something for you because you feel like there wasn't enough information and you are actually doing something better than we rated you, we're always open. I think what we do is we use the knowledge available to us publicly, and we have no shame in walking back on something we've said because someone provided data that we could share publicly that highlights how one of these things were wrong. And I think that's part of building the good faith in the community, which is if we want to be honest human beings and make sure that everybody has the right knowledge, we too have to be able to say, hey, we were wrong on this, they reached out, here's the real data, here's how it's doing better.
And now, at long last, I believe we are finally opening this up to questions. So now, all of those of you who've been keeping silent, let the flood open. Or don't, and we'll find things to talk about.
Yeah, I mean, I guess this. Here's a good question to the group. How do people feel about these two or at least the orthogonal approach? Like, let's start with the one we started with. How do people feel about the liquefied gas electrolyte? Where do people stand?
Checking chat.
Yeah, I have chat open on the side.
Oh, sure. I'll provide the links right now. They should be in the Battery Brunch notes section, but I'll drop them in the chat right now so people can get to them here as well.
Yeah, 100%.
Give me a sec.
But in general, okay, I'll start it off. I think, look, if I were South 8 Technologies, I think that's a much more, if I were somebody with money, which I am not, I would say, and I were somebody who was doing a new technology, like silicon or something, and I had my own pilot line. Like, so let's put myself, I'm in this figurative world. I am some silicon anode materials company that has a pilot line that can do manufacturing at the pilot scale. I would be chucking cells over to South 8 with like an NDA and just being like, please try things in here, right? It's a pretty low cost. They want to get entry into the market in as many technologies as possible. And then maybe you find something that's synergistic between the two, right? One thing that I didn't highlight in the talk, but when you have positive pressure, right, inside the cell, that really changes the dynamics of tortuosity and density of electrodes. When you go to these high pressure, right, so think about it. In normal cells in an EV, think of it as like someone giving you a hug, right? It's an outside exertion of pressure and things spill out. When you have positive pressure on the inside, it's like something is like trying to push out of your body, which is a very other disruptive thing. But the point being is in a cell, when you do something like that, suddenly tortuosity and stuff for wetting of the liquid electrolyte doesn't become as big a deal because you have a positive pressure function within the cell. So you can actually go and run higher density electrodes, which means you can make the jelly roll slightly longer, right? You can do all of these other things, right? Because in an 18650, for example, everything is a function of volume. Just my two thoughts. I would do that. Have money.
How does that work? So like if you're higher pressure, all of a sudden tortuosity doesn't matter?
So I guess tortuosity isn't the right word, right? Because tortuosity is just fundamentally of the travel distance between 2 points and how many turns you have to take. I would probably better characterize it as proper wetting of the entire electrode structure becomes less of a hindrance, right? If you're talking about, you're right, you're correct. Tortuosity is the wrong word here. It is the wetting.
Is it because like diffusion is faster in a high pressure gas?
No, the diffusion would actually be roughly the same. What happens is it's the contact angle between the surfaces of your liquid electrolyte versus the surface energy of your particle. If you have a positive pressure system, you kind of bypass that a little bit because you are forcing contact angles within the electrode architecture. So suddenly, if you have two particles that are impinging upon each other and there's this very little slot that you can't get through normally, a positive pressure system will force through, whereas a non-positive pressure system on the inside will the liquid will stay at the top, right? It won't want to go in, even if there is some small gap there. So that's really where they're leveraging. I think in the research I found when I was doing it, they can run, I think standard NMC cathodes are 27% is their porosity if you're talking about some of the tier ones. I don't know how close that number is. I think I'm in the ballpark, but I think they were running in the high teens to low 20s, somewhere in that range. So they were getting about 5% more. And just for everyone's context, a jelly roll is just a giant volume argument, or a 18650 or a cylindrical is a giant volume argument. It's just how much volume do you have available for you? How can you reduce the volume of things so you can shove more things in a very simplistic terms. So making your electrodes thinner inherently lets you to put more volume inside.
Jeff, don't you need a more strict construction of the casing?
So
the battery?
Yes, that was kind of what we highlighted in terms of the caps and the welding and stuff. There's going to be in the entire phase where you go for electrolyte injection all the way to sealing the cap or even just tab welding that cap, the lead to that cap when you assemble the cell. you're going to have very strong engineering practices in that, and you're going to have very strong and rigorous controls because you are playing with compressed gas, right? That is liquefied. Inherently, temperature is not your friend, and all of those operations tend to be very temperature high, right? If you're talking about, you don't want to run a gasket, so you laser weld, right? Instead of doing the standard crimp, suddenly a very low temperature thing getting introduced with a laser, those aren't really matching. So that, yeah, like you said, there's going to have to be pretty strict controls.
One thing
sorry. Go ahead.
I was going to say, one thing to highlight is while it is an issue, there are a lot of prismatic and cylindrical cells that are designed for things like, for example, deep earth oil drilling, where the temperatures get very hot and there's very high temperature and pressure. And so there is a lot of technology around more durable, more safe, higher safety feature, higher pressure enabling battery, cans and lids. So it's an issue, but it's not something that doesn't already exist and can't be maybe adapted. So that was kind of the thought process for why we graded it the way it was. It is an issue for sure, but it's something that's already somewhat addressed and available to piggyback off of.
Yeah, and just to answer this, guys, what do you mean by thinning down the electrodes? That's not the real world. It's densifying the electrode, right? Whenever we talk about an electrode thickness, right, we are assuming some amount of porosity. And if you take some of that amount of porosity out, you reduce the thickness and the overall volume.
Some advertising time here. We can engineer the porosity very fast and iterate very fast while doing that. Mm-hmm. So we should partner with Solar.
Yeah, I mean, I would say reach out always. I think you guys, if you look at it from the standpoint of all the technologies and the job market, there's a lot of very intelligent people with a lot of very interesting ideas. And I think we would all be hard pressed to say that if you took two different battery companies and had them actually work together, something useful and interesting wouldn't come out of it, right? I think something totally cool would come out, just because there's a lot of smart people trying to leverage different technologies, and I'm sure if you play the giant, mix and cross and match one of those has to work really well. So I mean, like I said, I think I'm all for companies holding their special sauce and not giving that away, but at the same time, any way you can kind of leverage the help of an established company, I would totally do. Like, for example, say your thing's electrolytes, right? And South 8's a liquid electrolyte, right? They should be calling CellGuard and being like, hey, we might have this disruptive technology. We can do separator wetting tests. But our version of a separator wetting test is probably not as good or as comprehensive as your version. Here's a liter of our liquid. In like the right conditions, all the safety. Can you please tell us what separator to use? Not only does CellGuard have a vested interest in making sure your technology is successful, it also then relieves resources from you, right? Because if this is the new hot thing, CellGuard wants to be able to sell, let's say, Tim at Tesla, kilometers of separator on the day, right? For this technology if Tesla ever decides to adopt it, right? So there's a kind of a synergy here, and it's all about leveraging, right? Soteria is a great example, and I think Aubert can expand upon that, on how Soteria actually leveraged industry to help advance their product.
So yeah, we did a previous talk about Soteria that got shortchanged because we ran out of time per usual. But basically what they have is they've got a coating technology that lets them put metal on both sides of the current collectors, anode and cathode, and also a safer separator technology. And what they've managed to do is they've developed it and patented it, and then they formed a consortium that has all of the sort of every step of the supply chain, raw materials to equipment makers, to the actual people that will produce the material, to the cell makers, to the end users. And what they've done is they've leveraged each of the people in there to help develop the technology with what they're good at. So they've got the equipment makers to work on how to better, coat the PET with the metal for the current collectors. They've gotten the supply makers to test it on their current tools to see if it works. They've gotten the cell makers to try using it on their current lines. And if they themselves, as a small startup, tried to do all of that, it's impossible. It would cost them so much money. But they found basically a way to incentivize all of these different levels of the industry to do what they already do, what they're already good at, what they already want to do with this new material. And so that's one of those things that I gave them a very, very high rating for surviving the Valley of Death, because basically, and also for engineering into the box, because basically they have gotten other companies that are doing what they do to specialize in to fund their own R&D on the materials. And so that's a great example of you leverage other people's interest to have them help you be successful so that you're successful and they're successful when you're successful.
Mm-hmm. I mean, you can track this to a lot of different battery companies, right? If you think about it, like if you are the coolest lithium metal making company in the world, right? And you have figured out how to make really awesome lithium metal anodes. I guarantee you there is a materials and a mining company that does nothing but produce lithium metal who has a vested interest in being your supply chain of like bulk lithium metal ingots. And they are somebody you would want to work with, right? Because why would you want to invent the wheel of, you go mine spodumene and do carbonate electrolysis, right? There's no reason for you to onboard that as a company, right? What you want to do is leverage what you have down below, right? And maybe as you grow bigger, you can then go your different ways as you try to bring that under the umbrella in an effort to reduce cost. But in the early days, Aubert and I are a big fan of cross-pollinization, right? You are cash and capital limited. Your goal should be to leverage everything you can for the lowest cost dollar at the best return, right? So, later everyone.
Can you answer one more quick question, Jeff?
Sure.
Question. You were saying on layer thickness, if you had thinner layers, you would get less voids, which makes sense so that you could increase energy density that way. But with the thinner layer thickness, you also have a higher, the metal layers are a higher percentage of your total battery pack. Are they not? And wouldn't that then theoretically also decrease the total energy density of the battery package?
So the way you think of a cell design, right, is two ways. You think of it as all the active components versus the inactive components, right? The active components can be lumped into your graphite or your NMC. Your inactive components can be lumped into your electrolyte, your separator, the metals you put things on, right? The casing, anything else, gaskets, etc. When you make an electrode denser, right, you are creating free volume within the cylindrical cell by which you can either make the wind, which goes in, which has more metal on it or more NMC on it, longer. Thus, you would keep the jelly roll ratio of actives to inactives the same, but the amount of energy going into the cell or active going into the cell relative to the case weight would be altered, right? You got to think of it on two levels. You may not change the ratio of actives to inactives in a jelly roll, but if you can fit more energy in the cell because you can make your jelly roll suddenly have a longer wind for your jelly roll because you made thinner electrodes, the case weight the weight of that becomes diluted to the energy you're putting in. Right? There's two layers.
What I'm saying is, are you considering the metal part active or inactive?
The NMC is the active part. The copper or the aluminum is the inactive part. Right? Tab welds are inactive.
When you're making the active thinner, isn't the aluminum thing
thinner is the wrong word, right? Oh, thinner is a result of densification, right? That does not mean the loading has changed. It just means you have reduced the overall porosity of the electrode, right? And in a cylindrical cell where volume is the biggest knob to increasing the amount of stuff you can put in there, densifying your components more gives you more free volume by which you can put more stuff in.
So you're densifying it, you're not making it physically thinner. I got it. That's where I missed it. That's helpful.
No, not a problem. Here to answer any questions. Aubert and I love to field anything. It doesn't have to be about these companies. You could have a hot take. We'll try and field it. We like anything spicy. It's all good.
Appreciate it.
Anyone else in the audience?
Are you familiar with the 24M technologies and how they are using this? They have the liquid electrode and then they have a solid electrolyte in between them. It's basically a mix between flow battery and a normal battery, but it's not using the flow characters, but they are using liquid electrodes in their system. So well semi-liquid.
Yeah, I was about to say let's classify liquid, guys. Liquid can mean a lot of things, right? Just as like gel can mean a lot of things. Gel could be a pudding, or it could be maple syrup, or it could be Jell-O, right? They're all gels, but they are very different levels of viscosity and rigidity, right? Juho, to reference your 24M technology, they are using something that is a liquid. It is a semi-solid though, right? It is more on the side of a Jell-O than it is on the side of a like flow battery liquid where you have, peristaltic pumps pumping liquid against two current collectors with an ion exchange membrane. So the reality between liquid electrolyte or electrodes and stuff is really just a play towards rates. Usually when you go the route of wanting to go with a gel or something of that nature, you're really going more towards your kinetics argument, right? What is the fundamental limiting factor? Or in the case of like a different chemistry, you are trying to inhibit something negative that is a result of, a liquid existing, right? So like, for example, lithium sulfur, why not? Liquids will dissolve polysulfides and those shuttle, right? So one thought could be you go with this semi-solid liquid electrode and you get enough electrical conductivity, but then you have a confined network by which you are trying to stop something from propagating. I'd have to do, honestly, a lot more research on the liquid stuff. Personally, just from the sound of it, it seems like a manufacturing nightmare. Because although if you could assemble like pouch cells by stack or jelly rolls by hand, having a machine doing this and then not deflecting the gel or semi-solid state over and over again in your assembly process seems like just a nightmare of like you're going to have cell performance deviation that goes like this, and your standard dev is going to be huge because maybe the pressure that the machine applied when it picked up the electrode stack was too much and it deformed the electrode surface of that semi-liquid state. A good example of this is, guys, it's like lithium metal is very soft, right, as we all know. So the vacuum arms that come in on like cell stackers for pouch cells can deform the lithium metal. And if you're talking about how a soft surface and deforming it, and one of the main causes of that surface going bad is any kind of deflection in it, this is just a process by which you create problems, right? So like there's a lot you have to think of in the tooling of this and what is feasible. Remember, our hands are a lot more ductile and versatile than a machine. And a machine doesn't have the sensitive touch that we do. So like you have to account all of these things when you look at these new technologies and how you're going to bring it into manufacturing.
But I've seen they are using very, very thick electrodes, something like up to 450 microns. And they are not stacking them. It's basically one electrode, but very, very thick electrode, and put that in a pouch. And then they have not disclosed anywhere what is the electrolyte. It has to be some kind of solid, yes, but I haven't found personally what kind of solid electrode they are using in between there.
Yeah. Aubert, you're muted if you're talking. We can't hear. He probably hit the mute. Oh. There we go.
Can you guys hear me now?
Yes.
Well, that's why I kept trying to cut you off and you wouldn't let me. Okay. So one thing I want to tackle real quick is that I apologize if I'm mispronouncing your name, but Guantum, actually, before he even said that, I wanted to bring up backtracking from the idea of whether it's liquid or gel or that kind of thing. Going back to solid state, one of the biggest issues from my perspective in solid state is a lot of people present things that are solid state adjacent, or as he put, semi-solid state to solid state. And so actual solid state, there's only really been like two of them, and it's been the Simbrex and the I might be mispronouncing that company name, but the ST Micro N film battery is one example of a fully solid state lithium metal, thin film micro battery, which is entirely solid state, no liquid electrolyte. And then the other company, like Simbet or Simbret, which had a similar one, which I believe has gone bankrupt since. But all of the other ones since then, Gotham. All right, thank you. Apologize for that. But the pretty much all the ones right now, they have a solid state component, whether it's cathode or anode or electrolyte or separator. There is a solid state component, maybe multiple, but most of them, if not all of them, also have a liquid electrolyte, which defeats the entire purpose of solid state from a safety perspective. And so to answer the question that was mentioned earlier is kind of yes. So There are other advantages to solid state in terms of rates, in terms of thinness, in terms of controlling literally atom orientation for crystalline structure as you make them, for example, for conductivity. Being able to make thicker lithium cobalt oxide, for example, crystalline, so it perfectly conducts. But the safety aspect of it, if you can make a safe liquid electrolyte, takes a huge sort of amount of wind out of their sails, because solid state tends to be more expensive for higher performance or some other premium. And one of those big premiums is supposed to be safety. And so if regular lithium ion cells with a liquid electrolyte are already safe, it takes a lot of the value proposition out.
Aubert, this is Karamjit. We do make true solid state, no liquids.
Okay.
And we also tested UL 1973, nail test, punch test, overcharge, heat next to a heat flame, no issue with it. So if you have liquids, you got problems. If it's truly solid state, no issue with it.
Absolutely. Love to open up one of your cells in our lab if they're for sale.
I'll give you some soon. Just
okay.
wait. Yeah.
Okay.
I want to also couch that, guys. Remember, when we talk safety, right? It's relative safety. Like let's not talk about, as I said before, if you're sitting on 100 kilowatts of energy versus 80, it's safer, but it's not safe, right? Like, those are the things we want to couch here. We got a chat, and since we're on the solid state section and wanted to talk about form factor, yes, solid state is currently limited to pouches, but that does not mean there doesn't exist a world where 18650s or cylindrical cells can become real. That is primarily going to be, in my opinion, a function of how they adhere the solid state layer and how thin they can make it, right? Because it's all about the radial bend. So, hot topic, 2 mil mandrel bend. That is the standard. If you can do a 2 millimeter mandrel bend, that is the standard by which you need to pass in order to make the requirements to go into an 18650. And if you start having delamination as a result of it, you fail. Solid state notoriously has not been successful in this category, but it doesn't mean it's not impossible. It just means there needs to be work put towards it. And I know that there's actually a few companies out there that are actually trying to go towards this route because as we've kind of all seen lately, prismatics and 186 or cylindrical cells are kind of the choice of auto manufacturers and a lot of other cell buyers. But there's a little bit of the wrinkle, which is in prismatics, you aren't constrained to a wind. BMW, notoriously in their prismatics, have actually run cell stacks, and they just put two next to each other, and then they get to choose if they want to run them in series or in parallel. So cylindricals, yes, you're going to have to pass that, and solid state will have a hard time, but it really depends on the form factor and internals of the prismatic when it comes to that, right? Because if they go with the two pouch stacks next to each other, it's no different than a pouch cell, it's just in a hard case. But if they go with the standard wind, then you'll also run into issues. So that's kind of the nuance there, right? You can't blatantly say solid state won't go into a prismatic because it really just depends on what the manufacturer is doing with it.
Yeah, we are just looking at pouch cells only, and they're so easy to make in that domain. So that's where we are heading to. Pretty large size pouch cells, and that's what our customers are looking for.
Yeah, that's a good fit.
And then we got another question about Scion Power. So Scion Power is another interesting company. Basically, if you read any of their literature, or if you look into them, they are a interesting, kind of got like an interesting genealogy. So if you look at all their patents, right, they started off with lithium sulfur, and they are the famous ones who developed the lithium nitrate additive. At some point, they shelved that lithium sulfur work and sold all those patents to BASF, and then made a killing off that probably. And when they started going up, they started doing this solid state technology, but that's not even really clear in itself. What they do is what they claim is their Lyceron layer is this solid state membrane, but they also have this lithium protected anode, right? Or lithium protection layer for their protected lithium anode on their website. So you kind of got to read between the lines. This could almost be something where Scion Power is saying, hey, we really like the voltage window for this solid state electrolyte that we're using, or this proprietary material that is a solid state. We don't know if it's oxide, sulfide, or whatever. but we're getting some sort of decomposition reaction between the lithium and that interface. So we're adding in this like buffer layer of thin buffer layer of material in order to essentially deter that negative reaction or any kind of parasitic loss. So reading between the lines, my guess is they probably have 2 layers in there. One is the actual solid state layer, and one is this basically like super thin membrane, ionically conductive membrane layer made of something different to stop any parasitic reactions of lithium against the metal anode, right? If I remember correctly, lithium stability, which one is it, Aubert, oxide or sulfide that it doesn't like?
Oh, sorry, my brain is thinking is on a different topic answering questions right now. I forget off the top of my head, I apologize.
It's sulfide that's not stable to lithium metal.
Oh, thanks, Andre.
Yeah, I think, and there is one similar patent from Oxys Energy as well. They have a geo coating on that, on lithium, that is also a lithium protecting layer. And for micro battery and solid state, that Symbet, I think you were discussing, that is already, they were outsourcing their batteries. Actually, they were having the technology. They have LCO LiPon based cathode, and the processing temperature was quite high, and then I think they were not really manufacturing that. They were just outsourcing their technology. Someone else was producing for them, and I guess last year the company is sold to someone else. This is the guess. I think so.
Yeah, I mean, one of those things, we haven't done Scion. So any of these other companies, we kind of gotta, we do these guys as like on top of our normal jobs. So we kind of do it beforehand, and we do a deep dive into their patents and their technology. But
and typically what that involves is us spending our, 8 p.m. to midnight the entire week before these talks, and so that's sort of our limiting factor on doing these.
Yeah, but if you guys have suggestions, I saw someone say 24M. If you want Scion Power, we can do Scion Power. If you want, the only one we don't touch is QuantumScape. That's because they're highly litigious, and we don't have money, or else this whole I would, if I had money argument wouldn't be a thing. So I don't want to be on the receiving end of that. But litigious just means they have lawyers and they will sue. And we want to avoid that.
If you say anything about them they disagree with, they are very quick to sue you as a company or personally. And Jeff and I both work for companies who we would get in a lot of trouble if we'd said something about them and their lawyers messaged our company's lawyers.
Gantam, we haven't experienced it, but we hope to never experience it. That is our end game. Yeah. So if you have a recommendation that isn't QuantumScape, we are probably going to be more favorable to doing them. We have a long list just to kind of give people some insights into what we have in the database for people to do. We got Aquion, Natron, Polyplus, Nanoramic, Nanotech, Brightvault, Factorial, Murata, Battereon, Prologium, StoreDot, Nexion, Genex. We have a whole database of all these startups that we track, and we actually create a list where we list their products and we list all the relative patents, and we have that whole database sorted out. So there's a lot in the bucket, but what I'm trying to say is if you want one of these before another, Aubert and I are open, right? We're here to help you out, so we don't mind shuffling things around.
The very next talk will probably be another one on cool technology, so we'll take a look at 24M, and if that's something that we think fits for their stuff, yeah, maybe that'll be one of the next ones.
Mm-hmm. So, I mean, I think...
Go
ahead.
Yeah.
I have a little question, so a little bit of a different topic than solid state, but it's entirely separate, but on pack balance. So something I just wanted to throw out there and discuss a little bit was cell-to-cell variances, and this could relate to solid state, but just talking with current technology. So an example is that I've heard about is older Model S packs still have a very high state of health per cell, like they have 90% state of health, but the whole pack goes bad, right? And it's because most of the time the cells get out of balance.
Yes.
So I'm curious if other people have heard about this, and what are some ways looking forward to prevent it and deal with those risks of the pack getting out of balance and
lawyers. So
or I mean on the engineering side, like what could be done to beyond putting a giant BMS that could handle, very high resistive loads if you're doing passive balancing, but how could you design your cells in a high C-rate application like an eVTOL to have even degradation between each cell parallel series pack, string, so that they degrade evenly instead of having this big imbalance? Because it's like cascading. You just keep having this cascading imbalance, and you need a huge BMS to be able to handle it.
Yeah,
I'm curious if you guys have heard some of that.
I can talk about this. So let's use the most famous car manufacturer of EVs right now. They're a pretty good gut standard. Tesla cells are plus minus 3%, right? If you look at their packs, they all perform plus minus 3% within each other, right? If you look at a battery from Panasonic or anyone else, they are also plus minus 3% of each other, right? Now, does that mean that the plus minus 3% is carried from the battery into the pack? Probably some of it, all of it is, but there's probably some other factor that is associated, right? So it's not you got a one-to-one translation. The issue you have, right, in the world, I agree with you, there could be a way that hasn't been discovered, but the issue, right, is if you're dealing with a plus minus 3 standard deviation between all cells, how do you organize them in such a manner? So in my mind, at the pack level, this would become from a sorting and filtering mechanism prior to installation in the pack. And that would be probably your best short-term guess, where you have a very quantitative way to say how close a battery will perform to another battery over 1,000+ cycles, which is very hard to do. Do not let, I'm casually talking about it, but do not let it fool you that being able to predict the outcome of a battery in a couple thousand cycles relative to another battery and have them be very tight within each other is an exceedingly challenging problem. Right.
But Jeff, so one thing to your point about 3%, right? If in each parallel stack they have 20+ cells, right? Whether it's Model 3 or Model S, they have a lot of cells in parallel. So even with that 3%, you're likely to statistically balance throughout.
So statistically, you may make the argument that you average out, but remember, just because you have a 10 in 11 chance of being correct does not mean the odds that you can't be wrong twice in a row, right? Remember, just because you have a 10 in 11 chance doesn't mean, if it didn't happen on the first time, it has to happen on the second time. It just means that it is highly unlikely for that event to occur where you don't get it the first and you don't get it the second, right? So even if you are making the claim that large amounts on the general average, you would get plus or minus 3 and you would balance out, the reality is you could get a bunch of cells that are plus 3, a bunch of cells that are plus 2, and a bunch of cells that are minus 1 and minus 3. And then you don't average, because remember, what you're talking about is the balancing between cells, right? So if you have a cell that's minus 3 and a cell that's plus 3 next to each other in the same pack, it's really hard to balance that because they are inherently already out of bounds with each other. And then as far as to the latter point of your question in terms of how do we engineering, actually there's a lot of people who do, the DIY that take apart Tesla packs. And the reason that Tesla and other EV manufacturers kind of basically shut those packs down the moment they detect a new cell is really for legal issues, right? If that cell is throwing off the overall, remember, when the BMS sees it, it just sees an aggregate voltage or an aggregate capacity, right? It doesn't see each individual cell's voltage or balance. It sees 20, like you said, or maybe it sees 10. If that one cell you throw in there pushes the average voltage up a little bit, the rest are actually being damaged more than the BMS thinks, right? So you get into this kind of catastrophic sense where over time it actually becomes really negative, right? And that's the tricky part, right? Because then who is liable?
Yeah. So there's a lot of things along this vein that people are working on right now. And I'm just going to throw out a couple, sort of big things. But, the idea of pack replacements, whether it's, you go to a gas station and your battery pack is swapped out as opposed to charging, or for vertical takeoff airplanes or other, vertical takeoff taxi cabs, right? The idea is you'll never be able to sit there and charge them long enough. But if you have them show up somewhere and you switch out the battery packs, okay, great. But if you're doing that, then there's a lot more impetus on the software, charging station, the BMS, and the utilization of the cells you have to take care of. And then in addition to all of that, the idea of second life for batteries, where you have to know not just what the pack did, but what every single cell in every single pack has gone through, so you can utilize it for a second market after its end of lifetime in EV, for example. And so a lot of work in all of these right now, and a lot of big questions that haven't been answered and problems that haven't been solved yet.
Right, like another one, a great example is if I handed you two 18650s without that really cool shrink wrap on it, right, and you're talking about second life applications, are they the same 18650? Right? Are they at the same light state of health? Right? Were they from the same application? Right? Or the same vendor? Do they have different lives?
Level, Jeff, on the pack level, like Aubert's point on, so one thing I've thought a lot about is, you know, the modules in the Model 3 versus Model S. If you consider the 14 modules in the Model S, you actually have the option to have each module be the same voltage, right? You could have each module be 400 volts. And that way, even if you have modules that are out of balance, then you could swap in a module that has less balance because all of your modules are in parallel. But it's a trade-off of then you have more series strings. So if one cell goes bad, then it knocks your voltage down. So it's like this risk-reward thing. But I do wonder, like in a pack like the Model 3, where you have 4 modules, maybe you could still have enough cells in parallel in each string to have each module at 400 volts. Right, because then you could really just swap out one, no problem. If it's not the same state of health as the other module, it's like no big deal. They're all in parallel, right? It doesn't matter.
Well, one thing I've heard of before for this specifically is that basically, you know, when they finish, you know, forming and then aging the cells, a lot of times they grade them. And if they had a better, longer, more expensive grading process, then they could actually take, you know, instead of just that entire group of cells goes in a pack, they go this one, this one, this one, this one, and from other lots, and then you put all of the exactly alike voltages in the same pack, and then control the pack that way. But that's more expensive and takes more time, and so people don't do it. But from like a performance perspective, what you're talking about, that would maybe make sense. And so maybe we'll see stuff like that going forward in the future. It's just more of it would cost them more right now to do it, so they're not.
Also, remember, the balancing is a function of degradation, right? I'm still surprised, and I think there might be a company that's doing it, that we don't see hybrid chemistries, right? Where you have...
Yeah, you have P and NMC or something. And...
Right, like if you take a note from the grid storage, right? If you have frequency and load balancing banks, right, you can suddenly say, hey, this doesn't have as much energy. Maybe my frequency balancing bank is just thinner electrodes, which are less prone to degradation, less prone to cracking. They may not give you the range, but then you run that in tandem with LFP, which are thicker electrodes, a lot more stable as a chemistry, and you can kind of do it. So, you know, I think that's an interesting area a lot of people aren't talking about, is taking the NMC. I think if I were to say the reason why, a company like that, to get the batteries needed from the manufacturers of good quality, they are a small fish, right? Battery industry is 11% margins, everyone. So like, one thing we notice a lot in the industry is that a lot of these, you know, EV bikes and stuff, they don't have the clout or the pull in order to get the supply of top tier batteries that they need. And not only that, they can't get batteries made to their specifications. They get kind of like the dregs of whoever was big that ordered for their application.
They're product takers, not you know, controllers.
Right. And remember, guys, in this world, and I want to stress this, in this world of batteries, the battery is the key enabler of the technology, right? The battery is what enables like a better pack, right? If you think about it like pack losses, it's due to rigidity. So you have some amount of metal. It's due to thermal. You got to have some sort of thermal balancing, BMS, all of that. If the cell is better, it takes away those constraints and enables a better pack. Similarly, right, like all these eVTOLs and stuff, those are all battery enabled. If you took your Tesla and you took out the batteries, does Tesla exist? They'd have this really cool electric motor maybe, but can they do anything without the batteries?
Yeah, you know, your point on the differing chemistries previously, you talked about like LFP and NMC. With the recent spike in the nickel prices, I wonder if we really could see a pack that's like literally like half LFP modules and then half NMC or something like that, where you could have a very small amount of, you know, your high energy density pack, and the only way you could do that is by having them be the same voltage, right, and having all the parallel packs. But I guess that is a big challenge on the reliability. Like, even to get with 2170s to get 400 volts, you need about 100 cells in series, right? So if you have 100 cells in one module, that's actually small. You could have 200 and then have at least 2 in parallel, which would give you at least 1 level of redundancy. But even if one of those cells fail, then you got a BMS problem, because then you really have to charge that one string a lot.
So thank you to whoever just shared that in the chat. So they just shared a Neo battery that has exactly that. They've got 2 different types of cell chemistries. They have an NMC and they have LFP in their battery pack.
Oh, boom.
That's cool. As of September 2021, that's actually really cool.
I am adding that to the list now that we speak of it, because that is exactly, we talk a lot about how we want to see that, and someone's doing it.
About this topic, I know that there was a trend like back in 2014 or something that you will take like LMO and mix it with LCO to get the price down and do it like the mixing on an electrode level. Is it done anymore at all?
Absolutely. So right now in commercial electric vehicles, what you'll see a lot of times is things like, for example, a little bit of silicon mixed in with graphite for charge rates on the anode, and you'll also see a lot of times there's different reasons, but you'll see like a little bit of 811 added into a 523 or 622 for a little bit more energy density, or other things like that for a little bit more rate, or whatever it is. So you will see, you know, the batteries on the cathode side have like, you know, 80-90% one material, 5-10-20% another material. So the answer is yes, and people are doing that for just getting whatever thing they need between those 2 different points that they can capture the best of both.
Mm-hmm. I mean,
cost is a big deal too.
Yeah, right. Like, margins are thin, so cost is really the big driver of a lot of things, right? Like, there is a world where you can just make really small particles, but the cost of doing so is exceedingly high, right? Like, making small uniform particles is not cheap. So like, cost is a big driver of a lot of these things, right? And then it's also cost related to consumer of that, not the consumer, us as the people, but the consumer of the actual battery. So like the Teslas and the Lucids in the world, right? They are what drive, which is actually, if you think about it, surprising, because packs are important, but grid is where the money is at, in my opinion. Crack the grid code. That's where you get your money. I think a hot take here is, guys, is everybody uses EV companies or automotive companies to gauge readiness of a battery technology. I think a battery technology that gets the, like, kind of the nod of the grid storage crowd, I would be throwing money at that in a heartbeat, because there's just far more upside. Like, grid storage, the market size is like 3 times that of the automotive.
Way more. So grid storage of electricity is a $30 trillion. So electricity costs a year. Grid electricity dispatch worldwide is $30 trillion a year. So even a small percent of that for storage is huge. It's just an enormous market.
Yeah, if you can disrupt that, then you're really talking about it, right? And remember, grid is a far different animal than EVs. EVs actually suck to design for. EVs are one part a consumer problem and actually all parts a consumer problem, right? We as human beings want more range, but we also want to do 0 to 60 in 2 seconds. And the batteries that enable that are not the same thing. They are very different batteries, and they have very different designs, and you cannot get both out of them. So not only that, automotive companies, to meet their demand, their margins are slim. So if you are a specialty product, automotive companies just want to beat you down on price, right? Like, that is their whole game. They don't have a ton of margin. So it's actually a really terrible place to shoot for, personally, as a battery company. Where you really want to shoot for is grid. Volume constraints, don't need to worry about it. Safety, people should not be inside of this thing or near this thing. It could be out in the desert. You got some temperature things you have to deal with, but that's okay. You can go towards pure load. You don't need to worry about doing pure load with pure frequency, right? Like, there's a lot of benefits to doing grid storage level.
And to caveat what Jeff just said, he means in terms of the largest markets to aim for, because obviously as a battery company also, there's a lot of smaller markets with very high margin returns for niche applications, and those are a perfectly fine place to be as well. You just don't get $1 billion of investment to scale for a $25 billion a year company. For that, you get $25 million for a $50 million a year company.
So Jeff, you mentioned Lucid earlier. Did you see the recent release by Peter Rawlinson on the cooling and his pack design? It was like a very detailed design about, he was talking about like coolant flow through the top plates versus the sidewall cooling. I don't know if, did you guys see that or?
So that is really dictated by the cell. So different cell designs, prismatic, pouch, cylindrical, all actually radiate heat differently. They have different heat generations. I think 18650s are through the axial plane. Pouch cells are through the edges. And I think, actually, Wes, I don't know if you were here last time we did this, but we were talking with Luke, I believe, about this. And we were talking about if you had, assuming all else are equal, like you could build the same pack, what form factor cell would you take? And I think we all said pouch, right?
Yeah.
Yeah. I think it goes to that, right? So my guess is Lucid is doing the top plates because they're axial heat generating, so they're cylindricals. So that's my guess. But
the other big piece of that is almost the entire danger direction for cylindricals is top up. They're basically shotgun shells, right? So they're also, in addition to making that a cooling plate, they're making it effectively an armor plate underneath the car so that you don't have them shooting up underneath the car. So that's another big piece of that.
How do you think the top cooling plate's going to play out on the degradation point? I know Lucid has like massive batteries that are like 120 kilowatt hours for their starting. But when they start to move to the smaller packs, do you think there's going to be any degradation? And like we talked about pack and balance between Lucid and Tesla's older cells, or do you think it's going to be pretty similar?
I think pack and balance is really just generated by the cells themselves, honestly speaking. I mean,
really not so much thermal or
thermal is a byproduct of a parasitic reaction, right? You don't generate heat just because it generates heat and then that induces a parasitic. It is because the parasitic reaction occurred first, which then generated heat, which then may propagate and create more parasitic reactions, right? So saying it's purely a thermal issue is kind of wrong, right? Because the heat wasn't generated until you had a parasitic reaction, right? So if you think about it from that standpoint, if you are always creating parasitic reactions, really what you're doing is you're trying to like corral people. And so yes, having better cooling will temper the problem, right? Because you are trying to stop the propagation, but the fundamental parasitic reaction itself isn't solved. Right, it's kind of band-aiding.
Yeah, balancing with the thermal. Interesting to see how it plays out with the top cooling versus sidewall cooling and other.
Oh yeah, items. I mean, as a if you think about it, all these automotive EV companies, how do you distinguish yourself, right? I think we would all here agree that driving, I don't know if people have it, but driving a V12 is different than driving a V8, which is different than driving a turbo 4-cylinder, which is different than, right? They're very different dynamics, right? Small car, big car, little car, boats, right? Like some people describe cars like driving boats, like old Cadillacs. Some people describe like it drives like it's on rails, which are small sports cars, right? But EVs unfortunately have the problem where linear torque feels linear regardless. Yes, I too am not rich. I just also pay for rentals. But that's the thing. No, but right, linear torque is the same, right? Whether it does 0 to 60 in 2 seconds versus 0 to 60 in 3 or 4, linear torque feels the same, right? I remember driving a Tesla versus a BMW i3, and although the Tesla throws me into my seat a lot harder, they both felt the same on acceleration. So suddenly it becomes, what is the differentiating factor for these EVs, right? And those things are tied to the battery. So the difference is, like you said, in sidewall versus top wall, right? If that leads to more stability and a longer life vehicle, people might gravitate towards it, right? Why do people buy Toyota Camrys? Because you could sink the darn thing and it would still turn over in the morning and keep going, right? Like, there is a factor of the market where all they want is a consistent, reliable product. So if your sidewall or top wall, whichever wins out, right, enables that kind of mindset towards the vehicle manufacturer, that is huge, right? because suddenly the performance is taken out, right? I don't care what you say. It all feels the same. The next thing is like, do you like the aesthetics, right? Like, is that the car? Some people don't care, some people do, and then it's also going to just be, what is the experience inside, right? I might be in the small world of people like this, but I am not a big fan of like just one giant screen in the middle and no like tack in front of me. It feels like I have to like peer right to do everything. And then two, I am also a huge not a fan of not having a volume knob. It's very simple. It was a very elegant solution. It turns, it moves the volume. I don't want to play like guess where my finger is on the touch screen to figure out what volume I want. I just want to dial. That's all. It's just the little things, right? Like, so I think the EV market's going to be interesting because yes, Rivian has a truck, Lucid has a truck or a sedan, and Tesla's going to have a truck, right? But like, I forget who I was talking to about this at Rivian. I asked them the same question, and then their response was just, well, we're the first in the truck segment. And I was like, how is that your differentiating factor? You were first to trucks? Like, congrats? That's what will make me buy you?
One cool thing about Rivian was they have the center layer thermal, so they have the plate, and then they have the double layer pack, which is the first we've really seen. I know Lucid has a portion of their EV platform is with the double layer, but because you have the truck platform, that allows you to have that double. So they claim like the highest energy density per volumetric space there. Mm-hmm. But it just seems like a great idea to have that cooling plate in the center, pack your cells closer, and then you just have one cooling plate for two sets of cells.
Yeah.
So the thing I keep waiting for people to care about, and we'll see whether they do or not, but when I look at packs like that, or like the Tesla one, which are basically giant ones with lots and lots and lots of little cells that are all either mechanically held in, or like the Tesla ones gooped in with that sort of thermal silly putty that they have, right? You basically cannot take out bad cells, and so you're replacing a pack. And the problem I see is that each of those packs is 10 grand, and if you have 30 cells that cost X dollars each out of 1 or 2,000, I would much rather be able to replace those, and there's no way to do that with the way they've designed it. And the other piece of it, so that's one piece of like going forward, replacement and maintenance of car over 10, 20, 30 years is not, I think it's not as economical as it could be, and they haven't had to deal with that yet, so they haven't therefore planned the extra cost to make it better long term in the short term. But the second piece is for recycling. It is going to be such a pain in the ass to recycle those packs versus you look at something like the Chevy Bolt with giant pouch cells, and literally you unscrew 4 bolts, you pull these long rods out, the entire thing falls apart into cells held in between dividers, and it took you 3 minutes to take apart 8 minutes to take apart the pack. It probably took us 45 hours to take all the cells out of a Tesla pack. And it was dangerous.
When I did the 444 cells, it took me 12 hours to use a router on the top and get them all out without nicking them and then testing them. But yeah.
Aubert does a lot of these pack. Like he tested the recent Mach-E or the recent Ford Lightning. Yeah.
Nice.
So like it's interesting for you to hear. He has a lot of good test data on that from Spectra. To answer someone in the chat, I agree. Heat generation is just current times the over potential equilibrium voltage versus OCV voltage. But remember, that's looking at it very mathematically. Why does there exist a equilibrium voltage versus a working voltage? Why does equilibrium versus working voltage even exist? Is that because that is just the equation? No, it's because the materials themselves are inefficient, right? And that is parasitic, right? You don't have in an ideal world, if you had perfect materials, you would have no resistance, right? So the sheer fact that you have a resistance load that you have to contend with is fundamentally a result of you having an imperfect material structure that is creating some sort of degradation mechanism.
So when on the thermal side, like you mentioned about the cooling loops, like they've moved from series loop in the Tesla to parallel loops from whatever I've seen in one recent model, I think it was Y article. But really challenges, right? Having each cell group have the same thermal, because you usually have 1 or 2 pumps, right, for your whole pack, and then you have your coolant flow through the channels. So I would assume that if you have a high C rate pack that's a smaller pack, it's not like a 120 kilowatt hour pack, you actually have a fair bit of degradation difference due to thermal, because it's really hard to get all your cells to be equally thermally monitored, especially if you live in a climate like Arizona where your ambient temperature is, 100 degrees for a good part of the year, right? So like, I do wonder, we're starting to see on the forums like TMC, the number of Model X pack failures at like 100,000, 150,000 miles is actually pretty high. Like people are posting like my pack's failing. So like I think that's a big challenge of manufacturers, how to get that temperature balance between the whole pack level.
I think it's actually a more interesting question is maybe a show of hands in the chat, but who here has actually driven a car to 150,000 miles?
I had, okay, so real fast. I had a 340,000 mile on the original battery Prius, and then it was at like 30% capacity and just died. It couldn't function anymore. And now I'm at 150,000 on my new one. So
but from an electric vehicle standpoint, like you could replace the battery, but that is a major, it's 20% of the cost of the car. Like I think we have to design EVs to go further. We have to get 200K or more, because it could go to the second owner and then keep going.
Well, the other piece of that too is that when you look at an environmental perspective, right? A battery through its lifetime is only more environmentally friendly than a gas engine at about 200,000 miles, and then assuming you can recycle it. And if you can't, it's less good for the environment. And so the entire premise of electrification being, to save the planet in some ways, it falls short unless you're getting that sort of 200,000 mile and recycling responsibly. And so I think we're going to see a lot more with that. The battery replacements during maintenance, the batteries through end of life, the recycling through end of life, and also now with all the material costs going up, companies are going to have to be able to reclaim their battery materials to go into the next generation, or they won't have the materials. So I think all of that is going to be interesting to see how people innovate to make that all work together, not just in the short term for profit, but in the long term for profit.
It seems like going to those modules and having at least like 4 modules of the same voltage, so you can literally just swap out one out of the 4, would help a ton, because like Tesla's talking about going to the single structural pack. Like you said, those cells are locked in there. There's no way you can just like extract one in any sort of a repairable format.
It makes it easier, faster, and cheaper for them to manufacture, but in the same way, it makes it worse, more expensive, and harder to replace things. Yeah, so it's a trade-off, and they're optimizing for short-term, not long-term.
Yeah, there's one thing that I've seen with EV. With Tesla, I think there's definitely that thing of the 8-year warranty. It's almost like the Apple business model of they want you to turn over. I think there is some incentive to want you to get the latest and greatest thing and upgrade. And that's sort of a conflict of interest, right? They're trying to bring the world to sustainability, but inherently in the business model, you have to have some new products and some turnover there. So it's a hard problem as a business leader, right? To balance those factors.
Right. Like if you think about it, public companies have like a legal obligation to their shareholders to do everything within their power to generate more profit. Right. So like, I hate to say this, but planned obsolescence is probably something that is taken into account. Right. I think, if you look at it from that standpoint, Tesla is probably looking at the math and just being like, well, if it goes 150,000 miles or 200,000 miles, the average human being drives their car X. We need to somehow generate money, but we're going to toe this line of like, we're trying to help the environment somehow, right? And I think that's where you get a lot of this like arbitrage in terms of, are they really doing like to the most ethical standpoint of helping the environment, can you say, right? Because like you said, right, like they're locked in, they're stuck, you're destroying frame if you want to change anything. So it really comes down to like the company has to be beholden to the shareholders, but the ideal of having this green and like right to repair and everything becomes a whole different subject matter, right?
The other thing is, you hear the million mile battery idea, and what that would be is it's a battery with a replaceable car. not a car with a replaceable battery pack, right? And that's a fundamental shift, right? And I think what's interesting is car companies would love that. Battery companies wouldn't, but car companies would love that. Oh, we get to sell you a new car every 5 years, and you pay for the battery pack? Yes, right? And the same sort of concept goes into a lot of the idea of the grid storage, at least for commercial homes, right? Whereas right now you kind of get 5 to 10 years maybe on your so energy storage unit for residential. But what you really want is you want one that will go 500,000 cycles and last you for 45 years, and therefore you can finance it like a mortgage. And if you leave that house, you will take it with you to the next house, right? And that's really where you have to have the long cycle life, the reliability, which takes you forever to do. But when you can hit those types of cycle life and timeline milestones, the 10, 20, 30-year ones, then you really start looking at the battery being the key thing, and everything else around it is replaceable, which we'll see if we ever get to. But
yeah, I mean,
it's a lot of discussion there.
It's kind of up to that, and it's also kind of up to regulatory, right? Like if you think about it, like I know I've said this in previous talks, and I think I pinged Aubert the exact ruling or law that states it from the FAA. But there is FAA out there that says, hey, if you do an electric airplane, you have to change your entire battery pack every year, right? That has zero to do with how robust the chemistry is, zero to do with anything. It has everything to do with regulatory. And people in regulatory, generally speaking, aren't battery specialists, right? So their viewpoint of what is good and good for the consumer is very different than what the battery scientist is saying, hey, what it can do versus is what they think, So it's a very complex web of things. And I think that as battery engineers, it's our job to just be really transparent and educate, because at the end of the day, it's the education of people outside of the industry that's going to help them better understand the challenges.
Or even people within the industry who don't have a technical background. And so I'm sure every single engineer here on this call and chemist on this call has had the experience of trying to explain to your marketing person or your boss or your CEO, it doesn't work that way. You can't do that.
Hey, a little different question on the
grid. They're engineers half the time.
Well, yes.
What have you guys seen on the grid storage for thermal regulation? I haven't seen many publicly posted articles, or what do they typically do do they liquid cool, and how are they managing?
It's the Wild West. Companies are getting ahead of regulations before regulations take place, and then it becomes this whole grandfather thing where are they still allowed to do it that way because they were ahead of the regulation? But frankly speaking, regulation, because it is usually on a cyclical thing of every few years is when new regulations come out that impact everything. Generally speaking, the industry tries to get ahead of said regulations, and then put it in. So I think it's a little bit of the Wild West right now, right? If you weren't a battery person and I said, hey, I'm gonna go drop 100 gigawatt or a gigawatt of lithium metal batteries in this area over here, and the person on the regulatory board goes lithium metal into Google, the first thing they're gonna see is fire, danger, all of these things, right? Regardless of what the actual case may be. So I think it's just the Wild West right now, where you got people who are sprinting ahead trying to push new technologies, and regulation is trying to catch up. You can probably draw a lot of parallels to the marijuana industry, not in the physical sense, but in the a lot of states went okay with it, federal wasn't, and then suddenly you had IKEA meatballs with cannabis. So kind of one of those things where it creates an issue where there's just the technology is moving so fast. Is it really feasible for regulatory to understand it, comprehend it, and understand what is best for that technology? Right, another parallel, not marijuana, is self-driving. Right, if you want to talk about a more apt parallel, let's talk about self-driving, right? There is not a ton of regulation around that. People don't know how to regulate it. People call their things autopilot or green cruise, right? And as a consumer, if you hear autopilot, everybody thinks they don't have to do anything, right? But that might not be the case. It could just be a level 2 software or sense of automation, right? Versus level 4, which is true self-driving. So like, it's one of those things where like, that is another great example of like, the technology is moving really fast. Cars can basically almost drive for very long periods unattended to, but the regulation doesn't exist to actually create distinct definitions of what counts to be true autopilot, what counts to be true self-driving, what counts to be partial, what is just really fancy, keep you within your lanes.
Well, I think going back a wee bit to the batteries lasting forever thing. I mean, working in solar, it's supposed to have like 30+ year life in solar panels, and now there's like a huge used market because the buildings don't last that long quite often.
Yeah. Yep.
You know, so it's really a cost equation of what's the cheapest battery technology I can get. If it only lasts 5 weeks, that might be fine. You know, lasts for 50 years.
The place where that, yeah, and you're exactly right. It's a cost equation, but the place that we see a lot of stuff is the cost for the technician to go out and replace it is often more valuable than the system. And so if you look at, for example, all of those, all the call boxes with the solar panels everywhere along the highways that all have batteries, the battery for that is like $40, but the call for the guy to replace the battery is like $800 to $1,000. So you would much rather pay 5 times more for a battery that lasts twice as long than you would for that guy to go visit every 2 years.
What is it? It is, what was the math, Aubert? It's like, dollars per kilowatt per cycle is probably that's the exact math you want.
So it's kilowatt. It's energy density, cost per cycle over lifetime is the equation, and you build into that the cost of replacements and stuff like that too. But yeah, if you have a battery that lasts a much longer cycle life, you typically cut out a lot of the maintenance and replacement costs associated with. And so even charging a premium there, it's still cheaper for the end user, and you can sell it.
Yeah,
I was going after Schneider on that account, because if Schneider do a lot of UPS stuff, which requires lead acid batteries, you have to swap out every couple of years. And I was thinking, okay, yeah, I'd much rather use my electric vehicle to power my home and my business, because they're being swapped all the time for me. You know, I don't have to pay for that piece if I'm using stuff that other people are cycling automatically.
Yeah, I think it's an interesting conversation just in general. What is the best metric by which you create the most accurate cost representation of what you will be doing, right? And how does it affect you, right? Because if it is cheaper, because there exists a world where it is far cheaper to have the guy come replace it because the thing is so darn cheap. Right, like the inverse is also true.
Or the labor is so cheap in that world, you know. Yeah.
Right, like a great example I will give you guys, I think, of like where a company intentionally did something somewhere else for their benefit was, I forget what it is, but it was one of the grid storage companies doing zinc flow batteries.
Yeah, they did it. I want to say, I'll find it, but I think it was somewhere in Africa.
Yeah.
And they gave it for free to the village as a tax write-off, as a donation, and helped them maintain it as a cost and a service, which had money. And what they got back from it is they got all the data from them using it, real-world use data in a real-world application over, it's been at least 5 years for it now, something like that. And so, like, that's invaluable. You can't pay for that kind of information, and they basically got it for free.
Right, because where else are you going to have such little regulatory concerns that you can literally be like, here you go.
Which company was that again?
Let me find it.
It's out of Tucson, or Phoenix.
I need to talk to those guys.
Hold on. It's
Flow battery.
Nant Energy or Fluidic. It's one of those two. Thank you, chat. Oh my gosh, lifesavers. They're the same. They're right. They changed names.
Okay. Yeah. All right. Great.
I have a question, guys.
Processor free since.
We are talking about making batteries repairable and all that. Like, I have a question on that. Let's say there's this cell. Battery is able to be repaired at the cell level. Okay. I swap out this faulty cell and I put in a new cell. The new cell will have a higher SOH compared to the other cells that already exist, right? So, and that would affect now the overall pack performance, because the new cell wouldn't never be utilized. The other cells would hit the lower limits and the limits set by the system. So how would we really want to do that? Want to do this repair service level serviceability at
the way you've described it? No, but what you would have to do is you would basically have to have every cell in the pack data in the BMS or other storage, and then every cell data in the new one, and the ability to balance, as we talked about before, or even you switch out the pack, put in a new pack and balance it that way. But then it's not a pack that's the size of half a car. It's maybe modular sub packs within a pack that you can swap out, something like that.
Okay, that was an example. Let's say I put it in a new module now, and the new module will never reach its there'll be some kind of energy and that'll be underutilized.
Yes, and then at the end of lifetime of that, then when that car is done and they're reclaiming out the batteries for recycling, they see, oh, that was, so like in a tire, your car is done at the tire, you've got 3 old tires, 1 new tire, maybe you take that new tire off and use it on the new car. That's maybe a bad analogy, but also maybe a good one.
Yeah,
where
I understand.
Yeah, and the thing is, to do that, you have to have almost perfect data of the usage profile to know what was done to it and how good it is, right?
Yeah.
From on a cell level, not a pack level.
Like we have that on a module level. Like we are building this NVMs into the modules, so they store data, and even in the wiring harness, and they store like SOH and those kind of parameters. So we know like when, and there's even talks of getting a battery passport, and that's coming with the regulation where if you want to recycle or install a battery somewhere, you can just like get this passport and get all the details. There are different parameters that's coming on that.
So it still might be like in your case, as what you said, like it might be the best option, right, to just replace that one cell and just deal with the fact that it has more capacity than the other cells. Like in some cases, like for an e-bike pack, right, you have one cell group that failed. Maybe just replace that one cell group and just let the other cells fall more than that single cell. So like in some case, it might just be the easiest from a serviceability point of view, right? Just like
yes. I understand, but then but as Aubert said, it would need proper features to track it, and that's what would enable that.
Yeah.
And I think more and more, especially as cells get bigger, which there's definitely a trend in large prismatic and large EV cells. When it's 10,000 cylindrical cells in a car, it's very hard and expensive to track it all. When now it's only 200 to 400 very large cells, it's not as hard. And I think you'll see more of that going forward on a cell tracking, large sub-module BMS swapping kind of stuff like that. But we'll see. That's just my opinion.
There's 2 trends right now. So there's another trend, which is how do you detect failures without as much equipment, right? And that's the gas sensor, because your gas sensing application for batteries, like lithium ion tamer is a great example of a company that does this, where their whole shtick is you don't need as much nannies in the system, because it can detect failure quicker in the system by sensing basically egress of volatile organics than it will show up on any kind of chemistry for a BMS. So you have a lot of competing trends where people realize it. I don't know if you guys know this, but the pack is 30% of the load in a Tesla, just the electronics and the pack itself to maintain it. So of your battery pack, 30% of it gets used just to keep it self-regulated, and then I don't even want to know how much self-driving or any of the autopilot features uses in terms of the battery pack's energy.
But that would be after the failure happened, right? Using the gas sensors.
Well,
I mean,
remember
if it could be more predictive, using by basing if I can detect it based on my usage, or my driving patterns, that would be more.
But you have to remember there's a cost, right? More analysis and data mining means more computational power. More computational power means less range. They're not in the business of less range, right? They're in the business of what gets me by, makes people happy, and gets me the biggest return. So yes, empirically, we could strap every cell in the pack to a monitoring system and isolate failures on a 1-by-1 basis. But the reality is that are they in the business to do that? Right, and that's.
I mean, the one cell parallel group, you still have the balancing. Like you find that one group of like 10 parallel cells, then like you still have a challenge, right? Because you have to go and disconnect all those 10 leads to figure out which cell might have brought that parallel stack down.
Yeah, that's cell level thing. But then I want to talk about this. It would be very hard to do it, right? Like, sort of. What good is it if I use gas sensors and after it had failed and it has degraded and I find it? Rather, I would rather prefer it to before the failure happens. If I can sort of restrict the vehicle's usage or something, the battery's usage into going into that situation.
So I would say empirically, right, gas sensors are being thought of because they're better predictors of failure than any kind of onboard electronics monitoring. Now, to your point about getting ahead of the failure point, right, we're talking about when it starts to go. I think that brings an interesting question, which is how do you predict the life cycle of a cell? Right? Can a cell with a 6% deviation from another cell, are you accurately able to predict within a pack balancing architecture the effects of different driving profiles by multiple thousands and millions of users on every cell within a bank?
I think the thing is you can do some of this stuff in electronics where you do Monte Carlo analysis. You need a model of a cell and the variability, and then you create lots of instances of that, and you kind of create smart models, and then you stack all your smart models together.
Yeah, but then like, what about the factorial equation that is the human being driving it? Right, like you can't predict the human. That's the problem, right? If we could predict,
I think humans are quite predictable. Humans are very, very predictable in a lot of their behavior. Particularly aggregated. That's very predictable. They'll do stupid things a lot of the time.
I mean, I would definitely challenge that notion, because if human beings were truly predictable, you would have none of the bad in the world that existed today, because we would always predict when there would be a negative outcome.
Oh, people tend to ignore the potential for the negative outcomes. You want to go through Freakonomics podcasts for
I love Freakonomics, but like I mean, to your point about that, right? Like, then how do you predict the people who choose to ignore, right? Like the as you keep going into the whole system step back, you don't win.
Yeah, it's like security. You can do security by looking for all the holes you need to plug, and then other people do security by saying you're not allowed to do that and hoping that people don't do it. There's generally no security at all.
You can have the technology to put a lock on it, right? Like you can control the system using technology rather than asking the driver to to stop using it or abusing it.
I mean, then you go into like self-driving, right, and fully autonomous, and then you get into the world where you have half the population who's like, I'm not putting my life in the hands of a computer, right? Whether I had an extremely and then you got half the population, right? Like, I think here's the thing, right? We've all been in a car and we've all stared at that other car on the freeway where you're looking at it and you are like, something terrible is going to occur, right? No amount of prediction is going to get you. That car. Yeah, or you've been in it, right? Like, no amount of predictive modeling will get you there, unfortunately, right?
I would tend to dispute that. I mean, people tend to limit what they model. I mean, I think one of the things with AI that's coming at the moment is that AIs are kind of unrestricted in what they can think, whereas humans are quite restricted. And there's a whole bunch of stuff on YouTube and 2-minute papers. And it's quite interesting how the AIs find the holes that humans would never think of and things. It's like
Having done AI, I can tell you right now, AI is kind of a misleading term. AI is just essentially, machine learning is even a misleading term. It's not like the machine is learning, right? What the machine is doing is going through several iterative loops over thousands and thousands of times to come up with a regression model that helps give them a prediction of what will occur within some tolerance, right?
You want to look at some of the 2-minute papers because they're not doing that. Sometimes they're playing games and they're trying to come up with strategies for things.
No. I mean,
they're trying to invent strategies rather than fit a model. So there's fitting the model stuff It's what you want to do for modeling a battery, perhaps. But then how somebody's going to drive a car, you're trying to work out what strategies are they going to use in different situations that you've never seen before. And the AIs can do things like that. It's just, it's like, I'm not sure exactly how you do that. But you need to have simulators for the AI to play in.
I think in a joyous sense, right? If AI was as truly as incredible as it were, we'd all be living our Skynet fears right now.
Well, it's not there yet, but I agree with both of you at sort of a middle ground of I agree, that it's heading to what you're saying, Kevin, and I agree with some of Jeff's skepticism about where it is now, right? But it's definitely interesting to see what people are doing with AI learning, even within the battery space. Like you look at a lot of the so the Mitra, the Will Chu group through Stanford, who is now Mitrachem associated, is they've done a lot of predictive analytics through AI learning, machine learning stuff on past cells through models, through can the model predict performance and things you haven't built or tested yet. And so stuff like that is an example. Or you look at automat solutions based on the matrix of experiments with a bunch of different electrolytes and a bunch of different chemistries, how can a computer go find ones that have not been tried or explored yet that will perform better within certain parameters, right? So it's all interesting stuff.
Yeah. But I would say in general, everyone, we've kind of hit that 2:15 cutoff that we try to strive for. I would say Aubert and I we are usually more than happy to go, but we also recognize that there's probably a good time to have a cutoff for these presentations, and we also know that Linda and
Yen need to close it.
Yeah, they need to close the whole thing. So I would like to say with this, great discussions all. Please let us know what you would like us to talk about. We're more than happy to chat anytime you want, and just reach out and let us know. Aubert?
I'm good. Yeah. If there's other companies you guys want us to do aside from 24M, connect with us at LinkedIn or send us messages at our Battery Brunch. Sorry, at our Battery Pack Discharging Monthly email. I'm happy to take recommendations and cover the stuff that you guys want to see covered. And one more time, so in both of our LinkedIn posts for today's event, in the notes on the Battery Brunch for this talk and all past talks, and also in the chat earlier, we posted the links to all of our previous presentations and all of our videos. And those will be good going forward. They're basically folders that will have all of them as we do them and going forward. So when we finish the video for this talk, for example, we'll throw it up there and you guys can watch it. And thanks for joining us. It was really fun today.
Thank you all.
Thank you guys.
Thanks, guys.
Thanks, Aubert and Jeff. You guys always do such a great job.